Um, Good morning or good afternoon to people. This is another in the series of the Camera seminars. And today's speaker is Jeff Donatelli. Jeff is the Deputy Director of Camera, and he's a mathematician who is one of the original founding members of Camera. And he's going to speak today on the multi-tiered iterative projection framework, how to exploit the mathematical structure of inverse problems to reconstruct complex structure from challenging experimental data. Jeff.
Okay, thank you, Jamie, and thank you all for coming today. So again, I'll talk about my work on developing this new mathematical and algorithmic framework to solve challenging inverse problems from emerging experimental data, which I call multi-tiered iterative projections, or MTIP for short. And so the reason how this all came about is just because over the years, I've sort of been tasked with solving a number of very challenging open inverse problems that could just not be tackled well through standard approaches. And this, for example, has included fluctuation X-ray scattering reconstruction, which is one of the main scientific drivers of the LCLS and European XFEL, and also a big part of the ExaFEL exascale computing project, where I'm working with people at SLAC, Los Alamos, and NERSC to be able to analyze LCLS data in real time. And so here, the 3D reconstruction problem, how you go from the data and reconstruct the 3D density of your sample, was actually a 40-year-old open problem. A related experiment is in single particle diffractive imaging, which is actually one of the main drivers behind the creation of the LCLS and European XFEL, and getting all this to scale nicely on big supercomputers to enable real-time analysis. The LCLS is, again, a key part of the ExaFEL ECP. And so here, there's sort of a big open problem in being able to scale to high resolutions and also match the extreme data rates produced by the free electron lasers. Another experiment is coherent surface scattering imaging, which is one of the main scientific drivers of the APSU upgrade and one of the main research focuses of Zhang through his early career project. And here, the 3D ab initio reconstruction problem, again, how you determine three-dimensional structure from the data, was a big open problem. And finally, this is something I did with John Spence in multiple scattering electron crystallography. Unfortunately, as many of you know, John actually passed away a few years ago, which is a big hit, a big loss for the scientific community. But I had the privilege to work with him on this. And so actually being able to solve this problem was one of his lifelong research goals. Basically, there's a big open problem in being able to analyze the electron crystallography data once your crystal thickness goes beyond about 10 to 50 nanometers due to the extreme amount of dynamical scattering or multiple scattering effects that occurs in the data.
Hey, how are you doing? Come on.
So basically, standard approaches just did not work well in solving these problems, and so I needed to come up with something new, and that's what I'll talk about today. So the general outline of the talk, I'll first start by giving a brief background on what an inverse problem is. Then I'll give an overview of the MTIP framework for solving complex inverse problems. I'll go through some of the math behind MTIP. And then I'll do a deep dive into a few MTIP applications to give you an idea of how this actually works. And then I'll briefly discuss some future directions. So what is an inverse problem exactly? So in general, the goal of an inverse problem is to reconstruct some physical model M. Often cases could be something like, say, the 3D density of your sample structure or its electric potential. But it could also be something like some kind of dynamic, some kind of diffusion coefficient, any kind of property that you want to recover about your sample. And you want to recover this physical model M from some set of measured data D about your sample. So for instance, it could be scattering or diffraction images, microscopy images, but any measurement you want to make about your sample. And you also typically want your model M to satisfy various kind of physical constraints, which I'm calling C. So for instance, you might want to enforce, say, a positive density, maybe some kind of symmetry of your structure, maybe some kind of sparsity, sort of things along those lines. So mathematically, this means you want to find an M that satisfies sort of two main constraints. A data constraint, meaning that your model M correctly maps to the data through some forward operator that I'm calling F here, where here the F essentially describes the physics in the measurement process. So for example, it'll mathematically encode the physical scattering process in a diffraction experiment. And then again, you also want M to satisfy various kind of physical constraints that you want to impose on the system. So there's tons of different flavors of inverse problems. Today, I'll mainly think about them in the context of imaging, but there's tons of other versions as well. So some common ones in imaging that you may have seen include things like determining 3D molecular structure from X-ray scattering, or constructing medical images from MRI, or extracting rock density from seismic reflection data, or reconstructing material structure from tomography. So essentially, in each of these cases, you basically want to go from some kind of data to reconstruct some features about your sample. And so there's been tons of research into figuring out how to efficiently solve these inverse problems over the years. And for a lot of these methods, there has been established algorithm and software out there to do this. So some of the standard inversion approaches include methods like direct optimization, which is probably one of the most common ones, where essentially you model inversion as solving this minimization problem, where you want to find a model M that minimizes the discrepancy between the forward model and your data. So you want to basically maximize the fit to your data. And then you typically add on some penalty term that I'm calling RC here to enforce whatever physical constraints that you want to impose on that model. And there's tons of different ways you can do this minimization. For example, using standard gradient-based methods, gradient descent, LBFGS, Hessian-based methods like Newton's method, randomized methods like simulated annealing, reverse Monte Carlo. If the problem is linear, then you can apply numerical linear algebra techniques. And there's tons of other ones that I don't have here as well that you could also apply. Another class of approaches is what I call application-specific techniques. These are methods that are sort of designed and tuned to solve specific experimental problems. So for instance, this includes filtered back projections for tomography, direct methods in crystallography, or holographic deconvolution in Fourier transform holography. Another class of methods, which is gaining more popularity recently, is machine learning, where you typically try to train, say, a neural network to directly learn the inversion operator, where you essentially try to train the network through a bunch of pairs of data and the reconstruction you want to spit out. And then the hope is once you train the network, you can pop in your new data and it'll magically spit out whatever reconstruction you want it to produce. And so there's something inherently wrong with all of these approaches. And for a lot of problems, they may actually be the optimal solution. But each one does have its own important limitations, which I'd like to discuss. So for example, in direct optimization, the gradient-based methods, they tend to have very slow convergence, especially if you don't have a good initial start. They also have a tendency to get trapped in local minima if your problem is non-convex. There are some hacks to try to escape those local minima, but if you have a bunch, that can be a problem. Hessian-based methods like Newton's method, they have much better convergence, but they tend to be very expensive in high dimensions. And what I'm referring to by the dimensionality problem here is basically the number of degrees of freedom that you need to represent your solution. For instance, if you want to recover the 3D structure of some kind of sample at a certain resolution, it would be the number of grid points that you would need to represent that structure on, say, a Cartesian grid. And so since you typically have to work with the Hessian of the Newton, that typically scales quadratically with the dimensionality of the problem. And so it could be, it can get sort of very computationally expensive really quick. The randomized methods, they actually do a good job at getting out of local minima, but they tend to have very slow convergence, which actually tends to get exponentially worse as you increase the dimensionality of the problem. Numerical linear algebra, it's perfect if your problem is linear, but oftentimes your problem has nonlinearities to it, or maybe you want to add a nonlinear constraint, in which case a lot of times these methods won't directly apply. For the application-specific techniques, well, the big limitation there is they typically don't generalize to new problems. They can also place limitations on the sample and measurement conditions. For instance, for the direct methods for crystallography, that typically only works if the unit cell for your crystal has less than about 100 atoms. Anything beyond that, you typically have to resort to other methods to actually get things to work. They can also have sensitivity to measurement errors and missing data. For instance, in the filtered back projections in tomography, that assumes that you collect projection images at a uniform set of different viewing angles of your sample. And if there's any sort of jitter or misalignment in that, or if you have gaps in your data, it'll produce large artifacts in its solution. And finally, it can be difficult to add additional constraints on top of what these methods already do. Usually they're sort of set up to directly go from the data to some kind of answer. And a lot of times there's basically no room to add any additional information into the process. For machine learning, one of the big limitations there is that for very complex inverse problems, you often see very poor scaling of the parameter and training data requirements. So a lot of times is what you see is you might be able to get this approach to work for inverse problems that don't have as complicated of a structure to them, or maybe you can get to work nicely for a sort of a low resolution answer. But as you start to increase the complexity and dimensionality of the problem, the number of parameters that you need in your network and the amount of training data can blow up and become sort of unmanageable pretty quickly. Another issue is they often have limitations on generalizability. So if you train the network on a specific detector setup at a certain resolution for a certain kind of sample, then if you change any of those parameters, then chances are you either have to retrain your network, or a lot of times you might have to come up with a completely different network architecture to get things to work. They also have a tendency to produce training bias. So basically, they have a tendency to produce an answer that's similar to what you trained it on. And then another issue is the optimal hyperparameter selection can be difficult. Basically, the solution can be very sensitive to how you design your network architecture and a number of degrees of freedom, and it can be very difficult to actually discover what that optimal architecture is. So again, there's something inherently wrong with all these approaches, but they each have their own limitations, which actually prevented me from using them on some of the challenging examples I showed you earlier. And so I had to come up with something new. And this is what led to the creation of the multi-tiered iterative projection or MTIP scheme. And so you can actually go to our website at camera.lbl.gov/software to see some specific implementations of MTIP. But it's essentially a modular algorithmic framework for solving complex inverse problems from data. And the way it works is by trying to exploit the mathematical substructures that are inherent in inversion by breaking the problem up into a series of simpler subproblems. And these subproblems are then solved essentially using the most optimal method available for each one, which you then encode as something called a projection, which I'll talk about later on. And so then what you do is you iterate over these projections to enforce consistency between the different solutions to the subproblems. And so I'll often depict these MTIP schemes through these complicated flow diagrams that I'll show you a bunch of as we go through the talk. Essentially, the different boxes kind of represent how you break up the problem, and the arrows represent basically how you progress through the iteration. But sort of the main idea is that if you want to solve a very complicated inverse problem, maybe those standard approaches don't work well to solve the entire inversion, but maybe they do work well at sort of solving certain chunks of the problem, certain subproblems of the entire inversion. So maybe, for instance, your problem is nonlinear, but maybe a big chunk of it is actually linear, in which case you can use tricks in numerical linear algebra to deal with that linear part. Maybe neural networks don't scale well to the entire inversion, but maybe they do scale well for a certain smaller part of the problem. And maybe you also sort of have some application techniques that you can sort of throw into the mix as well. But what MTIP allows you to do is sort of use those optimal solutions from some of those standard approaches all together in sort of one big unifying framework to try to give you the best of all worlds. And this is precisely when you want to use MTIP. If the standard approaches don't meet your needs, then you can start looking into the mathematical structure of the problem and then try to figure out, well, maybe you have tricks for solving different pieces of it. And then if so, MTIP gives you a way to sort of tie those pieces together in sort of a global framework. And I'll go through how this all works in more detail a bit later on. But essentially, by using MTIP, we were able to solve a number of important experimental problems that couldn't be tackled through standard approaches very efficiently. And so, for instance, this includes the examples I showed you before. For example, in fluctuation X-ray scattering, where here we use MTIP to determine the first successful 3D structures from experimental fluctuation scattering data collected at LCLS, also joint with people from European Exfil, ASU, Max Planck, and several other places. In single particle diffractive imaging, we were able to solve this using MTIP and basically provide high resolution structures with far less data requirements compared to previous approaches, and get all this to scale nicely on big supercomputers to enable real-time analysis of LCLS data, again, as a key part of this XFL exascale computing project with LCLS, SLAC, Los Alamos, and NERSC. We also used it to come up with the first method capable of determining 3D ab initio structure from coherent surface scattering imaging with APS and Argon. And there's the work I did with John Spence on multiple scattering electron crystallography, where this was the first method capable of extracting crystal structure from arbitrarily etheric electron crystallography data. And there's several other examples, including was the first method capable of extracting continuous densities, which are reconstructed from small angle X-ray scattering data. And here's an example that we did from data collected from the LCLS, and also joined with people from Max Planck. Also came up with a cool way to use MTIP to efficiently reduce and filter data. And here's an example of applying this to angular correlation data collected at the LCLS, also joined with people from European XFEL, and also applying this to the coherent surface scattering imaging data collected at the APS. Also came up with a cool way to use MTIP to more efficiently train neural networks as part of an LBL Early Career Award. Some other examples include jitter correction, tomographic reconstruction, which is actually led by Kanapriya Pandey, who's in camera. And she did this, and this was joint with NSLS2 and ALS. And she'll actually give a future camera seminar about some of these details, so please see that if you want to learn more. Also in conformational dynamics from diffuse scattering with ASU. This is also led by Kanapriya, who will talk about it in a later seminar. Another instance is this work by Zishi Hu, who used an MTIP-based scheme to come up with the first method capable of extracting rotational dynamics from X-ray photon correlation spectroscopy experiments joint with ALS. And he'll give a future seminar about this as well. And there's several related pieces of work. Some of these ideas were used in nanocrystallography and diffuse scattering with ASU, GSAX with ALS, and STEM holography with Peter Ursius' group at NSEM. So now I'd like to go behind some of the math involved in MTIP to give you an idea of how it actually works. So MTIP is based on this methodology called iterative projections. And what you do in these schemes is for every kind of constraint C that you want to impose on the system, you formulate what's called its Bregman projection operator, which I call P of C. And essentially what these projections do is they take some object X and some kind of constraint C that you want to impose on that object, and they project X to the closest thing satisfying that constraint. And so the thing is, if your constraint is set up in the right way, you typically have sort of nice computational tricks for very efficiently solving these projections. And I'll go through some examples of what those look like in just a bit. You can also generalize this definition as well. For instance, if you can't exactly satisfy the constraint C, then the projection then instead tries to compute some kind of least square solution. So essentially, it'll project X to the thing that's kind of closest to satisfying the constraint. So the way you can use these projections to solve a more complicated problem is, for example, using alternating projection style scheme, where, for instance, if you want to find some object X that satisfies two constraints A and B, what you do is you start by creating some kind of random initial guess, X0, and then you apply this iteration to it. So for each of the constraints A and B, you come up with their corresponding Bregman projections, so P of A and P of B, to enforce those constraints. And then what you do is for every iteration, you take your previous iterate, which I've called Xn here, then you apply the PA projection to project it to the closest point to the A constraint, and then PB to project it to the B constraint. And that gives you your new iterate. And then you keep going through this iterative process essentially till convergence. So you keep alternating between applying P of A and P of B. So here's a very simple example of how this sort of works. So here are constraints are for A that you lie on the blue line and for B that you lie on the red line. And so we want something that lies on both. So that's this purple intersection point here. So what we're going to do is we're going to take some X0, which I just happen to take at the bottom here. We're then going to apply the PA projection to project it to the closest point on the A constraint. And then the PB projection to project us back to the closest point on the B constraint. And then we project back to A, back to B over and over again. And so as you can see, we eventually reach our solution here. And now this is a very simple, trivial linear problem. And of course, there's better ways to solve this simple problem. But the nice thing about this approach is that it extends very nicely to much more complicated problems that live in much higher dimensions. We're being able to project to one of these higher dimensional constraint manifolds for this more complicated problem can actually solve a big chunk of the problem for us all at once. In some sense, kind of reduces it to the simple case of just bouncing back and forth between these higher dimensional complex constraint manifolds in higher dimensional space, which greatly simplifies the overall optimization process. One thing I'd like to point out is that this very simple alternating projection scheme is only guaranteed to converge to the global solution if your problem is convex, so no local minima. but there's lots of tricks that you can play and modify these schemes to escape the local minima. For instance, by replacing the projections with reflections, or using this trick called negative feedback, where you essentially add this term to the iteration that kind of blows up in just the right way if you start to get stuck in something that's inconsistent with the constraints, which eventually will kick you out of that local minima and sort of guide you toward the global solution. But I'm not going to go through those mathematical details of how you vary it today. So again, one of the most powerful features of this kind of approach is that you typically have sort of nice tricks for computing these projections. So I just want to give you some examples of what those actually look like. So one projection that comes up commonly if you're working with some kind of phase problem, so typically if you have some kind of scattering or diffraction data, is something called the complex magnitude projector. And so what you do here is you want to project some complex number z to the closest thing that has magnitude m. And so its projection is actually really simple. It just involves a simple renormalization of z. So you divide out by its magnitude and you multiply by the magnitude m that you want that. It's that easy. So graphically, this corresponds to taking z and projecting it to the closest point on a circle of radius m. So it's really easy to compute. Another very useful one is something called a support projection. And this ends up being useful if you want to say, for instance, enforce some kind of sparsity or a finite size on some kind of 3D density that you want to reconstruct from your data. And so here, what you want to do is you want to project some function f to the closest function that is 0 outside of some specified region S in your space. And so this is really easy to compute as well. You just take your function f and you zero it out everywhere outside your S region. So visually, it sort of looks like this. So this is your function here, where the dark blue is where it's 0, and in the middle it's non-zero. If you want to enforce this green support region on it, all you have to do is figure out where your object extends beyond that green box, in this case, and then just chop it off. So you set the density outside the support region to 0. It's that easy to compute. A few more examples, which are a little more involved, but we still have good sort of numerical tricks to compute, include a column spacer linear projection, where you want to project some vector x to the column space of a matrix A, which means that x is equal to ay for some vector y. This ends up being useful if A represents some kind of a physical forward operation, and you want to enforce that x is a legitimate output of whatever that physical process is. And you can write down this projection quite simply as simply the matrix A times its pseudo inverse. And then there's tons of numerical linear algebra tricks for computing the pseudo inverse, for example, using singular value decomposition techniques or iterative methods like conjugate gradient or other Krylov subspace methods. Another projection, which ends up being quite useful if you want to model noise in these projection schemes, turns out to be something called an ellipsoidal projection, where you essentially want to project some vector x to the closest point on this ellipse, where the coefficients of that ellipse are these wk weights that you see here. And so you can actually write down that projection quite simply as the kth component being xk over 1 plus lambda times wk. However, you have to sort of find this magic value of lambda, and that involves basically choosing a lambda that satisfies these conditions here on the right. So that basically turns the whole projection into a 1D numerical optimization that you have to do for lambda, but you can do this very efficiently, for example, using Newton's method. So again, this framework is very powerful because we typically have these nice computational tricks for very efficiently computing these projection operators. And so now I want to talk about how we can actually use that framework to efficiently exploit the mathematical structure of more complicated inverse problems. And sort of more specifically, what I mean by that is that you typically have a nice way to split up the forward operation relating the model M on the left here, the thing that you want to recover, and the data D on the right that you measure, through a series of sort of well-understood mathematical operations, which I'm calling these Fs here, which produce some kind of intermediate values, which I'm calling the Ws along the way in that mapping. And so these Fs are typically things you sort of have good tricks to deal with. And a lot of times they include things like, for instance, Fourier radon transforms, Grommet products, rotations, translations, things like that. And so the thing is, you typically have sort of nice mathematical shortcuts to sort of optimally deal with these subparts of the problems. For example, using some of the standard approaches that I mentioned earlier, or a lot of times you might even have analytical expressions for the solutions, like I showed you for some of the projection examples a few slides ago. So the thing is, essentially, most of the sort of direct optimization approaches are kind of inherently blind to the presence of these mathematical shortcuts that might occur in the middle. Because at the end of the day, they only look at how well the model maps to the data and then computes gradients and things based off whatever that difference is. And so they're sort of inherently unable to exploit some trick for one of these subparts of the problem that occurs somewhere in the middle. So what I'd like to address is basically, if you have these optimal solutions for subparts of the problem, then how do you combine them to get an efficient and robust solution to the entire inversion? And so this is what the MTIP framework seeks to do. And so MTIP essentially consists of 4 main parts. The first is decomposition of the forward operator, like I talked about in the last slide. And so here I just happen to draw this as 5 tiers, 5 boxes, but the number is arbitrary. It could be less, it could be more. It's just whatever you need to efficiently represent the structure of your problem. And I'll go through some examples of how you actually come up with that decomposition later on. But then what you do, once you have this decomposition down, you then recast inversion as trying to find as satisfying consistency between the different tiers, so that each of the M's or the W's correctly map to the value at the next tier, and also whatever physical constraints that you want to impose on the model M. So again, things like a support, sparsity, symmetry, things like that. So what this means is that you want to find an M and a bunch of W's such that each of these mappings hold, so that essentially f of 1 of M maps to the second tier, which is the W1 value, and also that f of 2 of W1 maps to the third tier, W2. F of 3 of W2 is W3, and finally you want f of 4 of W3 to be consistent with your measured data D. And also you want your model M to satisfy whatever physical constraint C that you want to impose on the system. And so once you do this, what you want to do is you then want to formulate Bregman projection operators to efficiently enforce all of these constraints in 2. So in particular, for each one of these tiers, each of these Fi, you come up with a corresponding projection P of I to enforce that constraint. And so in particular, what this does is it takes a previous estimate that you have for the corresponding M or W at that tier, and you project it to the closest value, the closest M or W, such that it correctly maps to the next tier. So in some sense, these projections kind of act like a pseudo-inverse, generalized pseudo-inverse to these Fs. For instance, if one of these Fs are invertible, the projection will just end up being its inverse. If one of these equations are underdetermined, then out of all possible solutions, the projection will give you the one that's closest to your previous estimate of M or W. If it's overdetermined, then as I mentioned before, the projection gives you some kind of a least squares solution. And then you also have projections to impose whatever physical constraints C that you want on the model. And so this is how we're going to try to exploit the mathematical shortcuts. If we have nice tricks for dealing with these subparts of the problem, we're going to try to encode those solutions very efficiently as these projections. And if you split up your problem in the right way, then you typically have very efficient methods for computing each of the projections, each of the P's in step 3. And so then what we do from here is we toss all these forward operators and all these projections into this big iteration. And so we typically start, again, with some kind of initial random model M. And then during each iteration, we take our current estimate for M, and then we propagate that model information forward by applying the forward operators. So we apply f of 1 to get the next tier W1, then f of 2, and then finally f of 3 to get W3. And then we save all these intermediate values as we sort of march forward. But now that we're at the end here, we then use these projection operators to project information from the data, propagate it back to update all the W's and all the M's here. So this means we then take our W3 and we project it to the closest thing consistent with the data through the P4 projector to get a new W3. And then we keep going back. We go back to W2 and project it to the closest thing that maps to this new W3, which gives us a new W2. And then we do this again to get a new W1, and then again to get a new model estimate M at the bottom left here. And then finally, we apply more projections to impose whatever physical constraints we want in the system. And then we just iterate over this process until convergence. So of course, I'm skipping a lot of the mathematical details here. You can do more complicated things than just tossing projections on top of each other. For instance, using the reflections or the negative feedback tricks I mentioned before. You can also modify this to model noise in the data, which is essentially involves replacing this equality with the data and relaxing it to essentially only enforcing that the output, the F of 4W3, satisfies some kind of statistical constraint relative to the data, corresponding to whatever noise model you think describes the noise in the experiment the best. But I think the best way to really understand this is just to really go through a few examples, which I'll do now. So the first thing that we came up with MTIP for is a fluctuation X-ray scattering, FXS, which I'll talk about now. And there's a ton of different people involved in this work, but some of the main collaborators include Kind Peter Pandey and Peter Zwart at Camera, Russell Kurda at European Expo, Mark Hunter at SLAC, and Wes Schlichting at Max Planck, and Rick Kirian at ASU. And so what you do in these experiments is you collect several diffraction patterns from a stream of mostly identical particles. They might come in different conformations, or maybe they're going some kind of dynamical change, but the structures are all somehow typically related to each other. And then essentially what you want to do is somehow reconstruct the structure of your sample from the data. One key requirement in these experiments is that you need the pulse lengths of the X-rays to be shorter than the rotational diffusion times, basically how long it takes for the objects to spin, to essentially prevent what would be rotational motion blur in the data, which is what you get in sort of traditional 1D SAC solution scattering experiments, if you're familiar with that. And so you can either do this by just performing this at a free electron laser where you have very short pulse lengths, or you could try to freeze the sample to try to slow down the rotation. But one of the cool things in this experiment is that the theory essentially works independent from the number of particles that you have in the beam per shot. And typically you want to pack in a decent number of particles in the beam all at once so that you get enough scattered signal from it to overcome any kind of background effects in the detection. However, this does complicate the data quite a bit, because this means your data now comes from the scattering of a bunch of different particles in the beam, all at its own different random and unknown orientation. So in some sense, the data is a bit scrambled. But it turns out there's a very elegant way to still analyze that scrambled data by computing something called the 3D angular cross correlation function of the images. Essentially, what you do here is for all pairs of rings in your detector, you compute the 1D cross correlation function between the signal at those two rings, and then you average over all of your images. And that'll give you a 1D correlation curve for each pair of rings at these different radii, Q and Q prime, in your detector. So that leaves you with a three-dimensional cross correlation function C, which you can then take its Legendre polynomial expansion of. And the reason why you want to do this is because those expansion coefficients, which I call BLQQ prime here, end up being very useful. You can actually show that they encode specific properties about the structure of your sample. And so you can essentially think of those as a series of increasingly higher order spectral surfaces describing kind of what your sample looks like. In particular, the L equals 0 term is the traditional 1D Sachs curve, but you can increase L to sort of get higher order information. I've drawn them here as 1D curves just to fit everything on the screen, but again, they're 2D spectral surfaces, since the BLs depend on the Q and Q prime, the pairs of rings that you use to generate it from the detector. But the big question here is basically, now how do you go from these BL coefficients and reconstruct the density of your sample? And this was something that was a big open problem for 40 years, how to actually do this. And this is what we came up with MTIP to initially solve. So ideally, I'd go through all the cool theory and math of how you actually derive the Ford operation relating the density to the BL coefficients. Unfortunately, there's no time to do that today. So instead, I'll just sort of tell you what those operations are. So how we go from the density row that we want to reconstruct on the left to the BL coefficients that we extract from the data. And so it turns out you can do this with four main forward operators. The first is you take the density row and you compute its Fourier transform to get what I call rho hat. You then take the squared magnitude of that to get the intensity I. You then take the spherical harmonic transform of that to get the spherical harmonic coefficients I, O, M, Q. If you're not familiar with what the spherical harmonics are, you can essentially just think of them as a generalization of the Fourier transform to the sphere, essentially. And then for the last step, it involves a Gramian product. So essentially, if you think of the BLs as matrices, so you index basically the rows of the matrix by Q and the columns by Q prime. And if you assemble these spherical harmonic coefficients into a bunch of matrices IL, basically rows indexed by Q and the columns by this M index, then you can actually show that the BL matrix is equal to this, what's called the Gramian product of IL, which is IL times its conjugate transpose. So now, for each one of these four forward operations, we need corresponding projections to essentially pseudo-invert them. So the Fourier transform, that's really easy. You just use the inverse Fourier transform, and we do that very efficiently using inverse FFT. The second step, that's just the complex magnitude projector that I showed you earlier. So that just involves a simple renormalization of the Fourier transform. For the third step, we have an inverse spherical harmonic transform, which is given by this summation here. So that's easy to compute. And for the last step, the Gramian projection, there's a lot of cool math in here that I really like to get into, but again, won't be able to due to time constraints. But sort of briefly, it involves looking at the eigenvalue decomposition of this BL matrices, and then the projection is represented as basically half of that decomposition times some missing unitary matrix U, which you recover by solving something called a unitary Procrustes problem, which you can do very efficiently using singular value decomposition techniques. But the whole point is we have good numerical linear algebra techniques for computing this projection, which is precisely what we want. And we have good tricks to efficiently compute all the other projections and all the other forward operators listed here, which is precisely what you want to make a good MTIP scheme. And so once we have all these operators down, what we do is we again toss them into this big iteration. So again, that means we start with a random initial density row. And then during each iteration, we take our current estimate of rho at the top left. Then we apply these four forward operators at the top to propagate information from rho to the data. And then again, we save all these intermediate values along the way. And then we apply the four projections in the middle to propagate information from the data back to update all of these intermediate quantities and ultimately update our density rho at the bottom left here. We then apply more projections to impose physical constraints, for instance, using the support projector I showed you earlier to enforce sparsity or finite size. But you can also add in positivity, symmetry, anything you want to encode. And then you just iterate over this loop until convergence. So here's some examples of actually applying this to both simulated and experimental fluctuation scattering data. So we first applied to this test case in trying to reconstruct this geometric shape on the left, just a ball with three objects cut out in the middle. And here's the reconstruction that we got from applying MTIP to its simulated data. And we also did this for a protein ion channel. So in the middle is the ground truth structure. And on the very right is the reconstruction that we get by applying MTIP to its simulated data. And as you can see, we get a pretty decent match to the truth in each case. But we also applied this to experimental data, joint with a bunch of different institutions that I've listed down here to help us set up the experiment, prep the sample, and so forth. And so we actually applied MTIP to get the first successful 3D reconstructions from experimental data collected at the LCLS. So here's an example of doing that in determining the 3D structure of a rice dwarf virus from single particle data collected at the LCLS. But then we also got this to work from multiple particle data collected at the LCLS, where here we had between 50 to 100 particles in the beam per shot. And so here's an example of doing this in the 3D reconstruction of a PBCV1 virus from its data collected at the LCLS. Another example I have to go through is in coherent surface scattering imaging, or CSSI. This is joint with Zhang Zhang, Mao Chu, Nicholas Schwartz at Argonne and APS. So what you want to do in these experiments is you want to collect diffraction patterns from a thin sample that's placed on some kind of substrate. But in order to get enough of a footprint between the beam and the sample so that you get enough signal scattered off, you typically want to perform these experiments using a grazing incidence angle. So in this diagram, that corresponds to having a very small angle, alpha I here. And also to get fully 3D information, you typically want to do the experiment in a rotation series, which basically means you want to collect diffraction patterns as you rotate your sample in plane. And you can also try to probe depth by doing the experiment with varying the incident angle of the alpha I here. However, due to the geometry of the experiment, the fact that you're using this very shallow grazing incident angles, this tends to produce multiple scattering events that greatly complicates the analysis of the data. So essentially what happens is due to these small angles, you tend to get multiple kinds of reflections off both the sample and the substrate. And what you typically see is you have these four main events that are most dominant in the data. So this first event is the normal sort of Born approximation term. This is essentially when the X-rays come in, hit the sample, and then scatter off directly to the detector. But you also get these other three events where, for instance, the X-rays come in, hit the sample, and then hit the substrate and then bounce off to the detector. Or they go essentially substrate, sample, then detector, or they hit substrate, then the sample, then the substrate again, and then the detector. So because of this, in order to model the data, you need to use something called the distorted wave Born approximation, which tells you that the intensity at a given pixel is given by the squared magnitude of this four-term summation, where this first term is the normal Born approximation term. This is just the Fourier transform of the sample density. And these other three terms consist of various shifts and reflections of that first term, and then multiplied by these R's, which are known as Fresnel reflection coefficients, which you actually know if you know the makeup of your substrate. So then the key problem is basically how do you go from this CSSI rotation series data and reconstruct the 3D density of your sample? And so doing this was actually an open problem. But we came up with another MTIP solution for this as well. This time it consists of these two main parts. The first forward operator is a non-uniform Fourier transform. The big reason why it has to be non-uniform is even if you can somehow structure your data on a grid, due to the shifts and reflections in the DWBA summation, those shifts and reflections can essentially take you off the grid, depending on what your exact experimental geometry is. And so you technically need a non-uniform transform to accurately model all the Fourier coefficients in the DWBA summation. But you can compute this very efficiently using non-uniform fast Fourier transform packages, so that's okay. The second operation is just the squared magnitude of the four-term DWBA summation that I showed you in the last slide. And so again, now we need corresponding projections for each one. For the first one, there's actually a lot of cool math in this, which is sort of a talk in itself, so I'll have to skip all the details. But to officially invert this, I actually had to come up with this new method that I call an optimal quadrature weighting. It essentially involves, at the very start of MTIP, pre-computing a set of optimal quadrature weights W, which just depend on how you sample your non-uniform sampling points of the Fourier transform. And once you have those, basically during the process, you can then take any non-uniform Fourier data at those sampling points, multiply it by those set of quadrature weights, and then directly compute the inverse to the non-uniform FFT through this adjoint non-uniform FFT that you see here, meaning that you can invert this linear operator directly without having to resort to any kind of iterative scheme, which might be quite expensive. So this allows us to very efficiently invert a non-uniform Fourier data, which is what we want. And then for the second operation, it turns out you can express its projection quite simply through this analytic expression here. I mean, it looks kind of complicated, but just a bunch of four-term summation. So it's really easy to compute that. And now that we have all these down, we toss them into the same kind of iterative loop that I keep showing you. And so here's an example of applying this to determine the 3D structure of a porous medium from its simulated CSSI data. So here on the left is the ground truth structure. I'm showing it at two different orientations just so you can see the full 3D-ness of it. In the middle is the data that we simulate from that. So this was collected at 3 different incident angles using about 1,000 images each in the corresponding rotation series. And on the right is a movie of the reconstruction that we get by applying MTIP to this data. So we just start with random noise, as you see here. And then if we let this run, as you see, it quickly picks up the main features of the ground truth structure. And then as we let this run, it just cleans things up a bit, and it eventually converges to a pretty good match to the target structure, as you see there. And then finally, I'd just like to briefly show you how we can use MTIP for data reduction and filtering as well. Sort of the key idea is, instead of thinking of using MTIP to reconstruct a 3D structure, you can think of our goal as trying to recover some kind of reduced form of the data from the original raw and noisy data. And so the goal of our inverse problem is to reconstruct that reduced representation. Another cool thing is once you have that reduced representation, you can map it back to the original data space, which will allow you to use physical constraints inherent in that mapping to remove noise and artifacts from the original data. And so here's some quick examples of applying this to experimental data in a coherent surface scattering imaging from the APS at the top and fluctuation scattering data from the LCLS at the bottom. So here in both cases, the original raw data is on the left. In the middle is what we get by applying this MTIP technique to filter the data. And as you can see, we can remove a ton of artifacts and noise from the original data. And on the very right is basically the reduced representations that we get from MTIP. Where here we're able to compress the original data by several orders of magnitude, in particular by factors ranging from 10 to the 3 and 10 to the 4 in this case. All right, and finally, I'd just like to talk about some future directions where some of this is going. So one of these include coming up with a machine learning augmented version of MTIP. So essentially what this means is, so in the examples I showed you earlier, we're always using these mathematical tricks to efficiently compute the forward operators and the projections. But what do you do if those tricks don't exist, if you don't have sort of fast ways to do that? Well, one solution might be to try to learn, say, a fast neural network representation of those mappings instead. And this will allow you to basically apply MTIP to problems where you might have good mathematical tricks to solve some of the subproblems, but not all of them. And on the other hand, this allows you to use machine learning approaches without having to possibly run into the issue of maybe it doesn't scale to the entire inversion. It's much easier to get it to scale for just certain subparts of the problem. So in some sense, this sort of combines both worlds of optimization and machine learning all in one, which can be very powerful. I'm also constantly on the lookout on trying to figure out how to mathematically encode new physical descriptors of constraints and projections within MTIP, and also try to learn new constraints from databases of objects using machine learning techniques and tossing that into MTIP. I'll also try to incorporate iterative detector artifact modeling within the inversion itself. So it might almost seem like, based on how I presented things, that we just took the data right from the experiment, threw in the MTIP right away, and everything just worked magically. That's not the case at all. It actually required months to years of hard work from a lot of people to sift through the data, figure out all the issues with it, recalibrate things, remove artifacts, remove bad images before we could actually get things to work nicely. And I think we could greatly expedite that whole process if we could figure out a good way to combine that whole process inside the inversion itself, which would also allow us to use physical constraints inherent in the inversion that help us figure out where those artifacts are and help us figure out how to calibrate, how to clean up the data basically during the inversion itself. Another thing I'm looking into is, as I briefly mentioned earlier, MTIP is currently implemented in sort of a very application hardware specific way, basically just whatever we needed to meet the experimental needs of those specific applications that I showed you earlier. But I'd like to generalize this into a more modular MTIP software library, basically a library of common forward operators and projections that could greatly expedite the creation of new MTIP schemes. And finally, I'm also always on the lookout for new problems, new experiments to apply MTIP to as well. All right, so I'll pretty much stop there. I'd like to thank all my collaborators that I've listed here, and finally, thank you all for coming today and for listening. I'm happy to take any questions.
Okay, thank you, Jeff. We can try raising hands, or people can simply jump in with questions. Hans Johansson.
Hi, Jeff. Thanks for the talk. That was great.
Thank you.
I saw a familiarity there with all the projections and your mentioning of the SVD algorithms and things. For some of these problems with machine learning, do you know how because the projection's nice in that it's bounded, right? You kind of have a projection magnitude that you can avoid overshoots with. How would you encode that in machine learning algorithms that are kind of fully nonlinear and where you might be worried about wandering off your manifold of constraint?
You mean how to make machine learning more like the projections, or?
Yeah, more like projections, and also specifically like bounds preserving, for example, or positivity or things like that.
I mean, that's sort of a big research question. What's the right way to do that? I mean, my most natural thought, like when I'm talking about the ML augmented MTIP, is basically just try to train the network to essentially act like a projection. So basically try to penalize it from producing large perturbations in the actual training procedure. But that's the details of that is sort of a probably multi-year research project. But it's a very interesting question, though.
Yeah, and I've been looking at it too, because a lot of trends in constraint-based or physics-based machine learning are running into that problem, right?
Yeah.
Overshoots and projections and bounds preservation. Thanks.
Okay, other questions? Abe.
Hi, yeah, I found this super fascinating talk. I had a quick question, which is that I noticed that in the MTIP framework, you regenerate the intermediate variables from the basic data at every iteration. So there's this full loop. I'm curious if you've spent any time trying to allow those intermediate variables to float, like you might do in a sort of augmented Lagrangian, I guess what it's called, method.
Oh yeah,
and sort of separately constrain those intermediate variables.
So a lot of times that comes up naturally, especially if there's big if you have sort of gaps in your actual data. Like to solve those forward steps, you might compute a 3D Fourier transform of something, but maybe you don't have diffraction data sort of constraining all the values of that Fourier transform in all your 3D space. And so what you do there is precisely what you said. You sort of allow those things to float. And so that there's sort of element of that in sort of all the examples I showed you earlier, because we always do have some elements of missing data, and so we do have to allow a lot of things to float along the way. The key thing there is if you do that, you have to be careful to make everything as stable as possible, because if you don't have any if you don't constrain the floating elements, there's a tendency for it to sort of get out of control. So you just have to be careful to make sure you're not introducing any instabilities in any of the steps.
All right, thanks.
Thank you.
Other questions? Philip.
Hello, thank you for the nice talk. So one question I had about in the section about the alternating projection algorithm is it possible in this context to accelerate that with something that I guess converges faster with respect to the number of steps, such as conjugate gradient, without substantially increasing the cost of solution?
I mean, yeah, for the very simple 2D problem, yeah, I mean, that's exactly what you would do. Figuring out the right way to generalize that to general projection method is another thing I've been looking into. I haven't found a good approach to that yet. There are a lot of general acceleration schemes where you throw in what your maybe the last few what you got from the last few iterations into it, and it's supposed to, once you do that, it'll give you something that's supposed to accelerate the overall convergence. But I haven't found anything that works quite yet. But that's another sort of research direction I'm looking into, which I think is quite interesting.
Thank you.
Thank you.
Okay, Timothy.
Yeah, Jeffrey, I wanted to say, so this was a really interesting talk. My background's a little bit different. So I'm a particle theorist at Argonne, but we often engage in calculations not unlike what you've talked about today. I mean, we in general have some large multi-dimensional model that we would like to constrain to the world set of high energy data, and it's its own very complicated inverse problem. In this case, where we'd like to determine some sort of multi-dimensional distributions. I'm wondering if you've considered, this is a very general question, but if you have considered it, sort of extensions of what you've talked about here today, because indeed, exactly as you talked about in your introduction, there's usually some mix of Hessian or Monte Carlo methods or something involving machine learning, each of which has its own advantages and disadvantages, and some sort of hybridized approach like you've talked about would be really interesting and compelling. So I don't know if you have any reactions to that. I mean, much of what you talked about in terms of applications today was these sort of diffraction experiments, which are not unlike what I'm talking about in a way, but to what extent could you envision this framework sort of generalizing to just general problems in mathematical modeling?
Yeah, it's it just, most of what I worked on happened to be these diffraction experiments. But I showed a few more abstract things like the machine learning example earlier on. There's no limitation to those traditional imaging techniques, and yeah, it's sort of a global framework just for any kind of inverse problem. And so the stuff you just mentioned actually sounds pretty exciting. If you want to send me some details, I'd be happy to look into it.
Yeah, excellent.
I think it
Thank you.
extends to all those kind of problems. Basically, yeah, if you have these complex structures in the inversion framework, that's when this sort of MTIP based approach is good at. It's not limited to sort of imaging things at all.
Right. Thank you very much.
Thank you.
Okay, Adi.
Hi, thank you for the very interesting talk. I'm from Slack. My main interest is ultra-fast scattering, and I just actually finished some research on super resolution in scattering. And so I'm curious about a few things. So I'll just ask a couple questions and not two more, because I have so many. An example of a question is, in this multi-tier approach, once you select, let's say, a prior or some constraint, how does it serve? For example, if you do a sparsity type prior, this can or cannot lead to super resolution. This is why I'm thinking about this. But the details about how this is preserved are highly dependent in other factors like the discretization or the noise. And so as you go from one tier to the next, how would the approach will stabilize that, or will keep that property of the prior or the penalty that you're using? Or is it something that needs to be tested per decision on what type of constraint are you using?
That's a good question. A lot of it boils down to just formulating each of the operations in a consistent framework. I mean, so one common thing that can mess things up is if for some reason you need to change grids along the way, like go from a Cartesian grid to a polar grid to something else, then some of the information might get lost in that interpolation process. So it's usually, if you want to preserve that information, you have to find good tricks for basically coming up with the consistent mathematical formulation as you go from each step to the next. That's the main thing.
You said that because you mentioned non-uniform Fourier, right?
Yeah.
But if your grid is non-uniform, you can then leverage compressed sensing type approaches, because you can basically have off the grid or higher frequency type of information that would, because of the non-uniformity, you wouldn't otherwise access. So I don't know if that automatically gets into that process, or do you need to somehow amplify or understand the effect that such an approach has on, for example, discovering higher or resolution information, etc. This is like an example of what you said on this non-uniform Fourier that you mentioned.
Yeah, that's a good example. So yeah, once you have non-uniform Fourier data, and like you said, if you have sparsity or finite size, just some kind of size constraint on your sample, that's actually enough to produce essentially arbitrarily high super resolution, depending on the sampling rate of your non-uniform Fourier data. The only big limitation there is mathematically there's no limit to that. If you sample the non-uniform data at an infinite rate, you can go to arbitrarily high resolution. The limitation is that the stability starts to go out the window at some point. If you try to get too much, that inversion just becomes unstable. So
Yeah,
if you want to try to recover as much super resolution as possible, it's just a matter of trying to be very careful about how you do that inversion in the most stable way you can.
Okay, we have time for one more question. Khalid?
Yeah, thank you for a great talk. I just had two quick questions, but maybe I'll just compound them into one. The first one is, how do you deal with time-changing constraints? So let's say you're solving a dynamics problem where your constraints change from time step to time step. I was wondering if your MTIP code can maybe is it modular enough to change one constraint and swap one out instead of another and still be consistent? And the other quick one is, do you have a comment on how the uncertainty propagates over your different operators or your different steps of your approach? Thank you, buddy.
Yeah.
It's a great talk.
Yeah, thank you. Yeah, the first question, yeah, that's a very interesting. I haven't thought about how to. I mean, I haven't really thought about it in that context, but in principle, if your constraints are changing from one step to the next, you can easily just replace them. As long as the constraints eventually converge, then your solution should converge as well. So I don't think that should be a fundamental issue unless your constraints are bouncing all over the place. And for the uncertainty propagation, so figuring out how to do that in the most elegant way possible to propagate it from tier to tier is something I'm still looking into. What we usually do is actually pretty simple to model the uncertainty. Is we typically just run the if we have experimental data, we'll rerun the reconstruction several times using different initial starting points to sort of sample. Basically sample the distribution of possible solutions, giving some kind of uncertainty model that you impose on the data. But we haven't done anything more sophisticated yet, which I think is another good sort of research direction to look into.
Okay, Jeff, let me end with a really silly one. I can't figure out whether breaking this thing into subparts makes it easier or more impossible to debug. Can you comment on this?
Yeah, maybe that is the one downside of it. It does make it harder because you have to make sure, like if you do unit tests or something, usually what you do is a unit test for each subpart. And a lot of times what you might see is each unit test works out, but there's some small bug or instability in how the different parts talk to each other.
That's what I'm worried about.
And so finding those bugs is probably the trickier part in this whole thing.
Got it. Okay, we're just about a second or so over, so let's thank the speaker and thank all of you for joining. The video of this will be posted on the Camera website under seminars, and Jeff's email address is easy to find on the Camera website, etc. Thank you to the speaker and thanks everybody for coming.